Okay. Hope I'm audible. Am I audible or if there is any issue on my side? Okay. I'll start from where we left out in the last part of the session.
Is it Himanshu going to join?
I think Himanshu will be like available within 5 to 7 minutes. So yeah. Hope you guys could see my screen now. So yeah. So from the state space model, the state space model which we are speaking on, in the S4 they actually proposed two sides, on the recurrence side as well as on the convolution side. So in the last meeting, I kind of like said whether how the uh, state space model works primarily. So everybody was present, I guess, or can I just give you an intro over there? Mm, okay, I'll just give you an intro. So this is like the first S4 paper. Before that, there were like a lot of other recurrent neural network architectures, which were kind of proposed alternative to the transformers. But state space model uh, gained its popularity or uh, gained its gained its popularity, or why people think state space model is feasible because state space model runs really well with minimum number of parameters as well as give you robust features with the minimum number of parameters available. If you look into transformers, it's just computing an attention grid of size n comma n, and then you're using uh, values to convert into the data which was given before. So instead of I kind of say that process is more like a brute force one because like you're computing the entire window of attention at the time as well as you are applying value towards it. So if there is any way to minimize the parameters into some form and apply some kind of attention, but not exactly to it, apply some kind of attention and get some results out. So that's the motivation of state space model. So this is the S4 paper proposed by Albert Gu et al. So this is the simple architecture. So on the let me check whether I get annotated tools. Give me a second. Mhm. Give me a minute. Okay, I'm not using the app so that I couldn't get the annotation. I'm just looking. Give me a minute. Give me 1 minute. Okay, I'll just convert this into PDF and just.
We can see the slides. So,
Oh yeah, you could see this. Like I wanna kind of annotate it. Like it will be more.
okay, okay.
I'm
Intuitive,
sorry.
yeah.
Yeah, ocular like that's the best. Okay. Yeah. So yeah, best. Yeah. So like speaking on it, just hope it's visible. So okay. So first thing like okay, let me say about something called continuous distribution. So in the continuous distribution, like you will have infinite number of possible values present into infinite number of possible values present into a distribution. But is the data which we are like giving whether it's an continuous distribution? That is not, because even though text or an image, it could be said it's kind of present into some large discrete distribution rather than say it is a continuous distribution. So what they did is like it's not only like you just initialize parameters A, B, and C and D. You also discretize them. That's the key point on state space models. So on the S4, instead of like making A as some kind of parameter, which they eventually did in Mamba, but we just take it in the context of H4, S4. They initialize hypometrics, and with the hypometrics, uh, also the B is some kind of like normalized matrix, not much of an diagonalized parameter matrix, and C and D, C is also parameter, and D here is eventually initialized to like 0, like you don't do any computations with D, so you just ignore it. So if you know about like some kind of control theory, like you are controlling the factor of the input which is coming into, uh, you are controlling the factor of input, let it be U, uh, into some kind of kernel, like I'll come upon with kernel soon. So first thing you initialize parameters. Second thing, you discretize them. Okay. On discretization, eventually in the course of state space model, they eventually did two types of discretization. First thing, uh, zero order hold methods, either bilinear or exponentiating the delta parameter. So in the discretization, what you do is like, I have a continuous distribution. Let it be some p of x. So I can't like put the continuous distribution into this thing, but I could convert it into some group of discrete distributions with a step size of delta. Hope it's understandable. Like let's take this Gaussian curve. If I'm discretizing it, like let my delta be some kind of like 0.1. So at intervals, I'll make this, say this is a discrete distribution at the time step. The time step won't be like this much large, like time step will be really, really small. So eventually I could convert the continuous representations on the parameters into discrete representation with delta parameter, either bilinear transformations or you use exponentiating. That's up to the exploration point. You discretize it, and then let it be x. and then you apply the recurrent point of view. K plus 1 is equal to xk, and u is like input of the uh, input of the oh shoot, I'm stuttering, sorry. K is the current time step, u is an input with the b matrix, and a is also a parameter. Like you're doing more often like forgetting what to forget and what to remember as an LSTM. More like a forgetting gate and remembering gate. And on the Y, like you add another gate, which is C parameter in this case, and you take a softmax of it, or what else we want to do. Like just like in LSTM. Hope it's like understandable, guys. Is it fine or? Okay. So this is what I said, like take parameters A, B, C, D, and discretize the parameter either bilinear or exponentiating with a delta parameter, which is not a zero order old method, and convert those continuous distributions into discrete, because in recurrent we feed the discrete as an input in the case of classical RNNs. Yeah. Whatever I said like in the before, it's the same over here. So, okay. So in the S4, we have this recurrent formula. Xk will be A times xk minus 1 and B times uk, and yk will be C times xk minus C times xk. So what you do is like you convert this into discrete formula, like the continuous A into discretized A by applying bilinear transformation. I think like I sent the proof over on our Discord channel, like how this bilinear transformation is applied. Hope you guys can look into it. So first, what they do is like I'll come upon with the first thing. You take input sequence, let it be u, and you discretize it. If it's I'm talking in the case of continuous state, continuous state. So you discretize it. Uk will be some kind of like up to delta parameter. So if you are discretizing this, you have to discretize A2. So A will be discretized with the identity matrix minus the delta by 2 into A inverse, the same thing. The same thing here with delta B, and C is just C here. So is it like fine, or like you need more explanation? Guys. Okay. So the hypo matrix is defined as this. The each entry is like you'll make an diagonalized matrix. If you look into appendix of this paper, you'll get to know it. So okay. So this is a recurrent. You could say this is an recurrent representation on kth time step. But if you keep on like doing this recurrent convolutions back by back, recurrent computation back by back, you could eventually put them into one tensor and just multiply with x. So that's eventually what they say as a convolution filter on S4 models. So this is the kernel, and if you want like y equal to x, so that is it. So this is the kernelized version of it. So this side, like there is two sides coming from this, either the recurrent one or the convolution one. So in the recurrent one, like we saw, xk will be some kind of recurrently dependent equation, But in the convolution one, we stack all these recurrent connection into one kernel and convolute it with the U. The U meaning the uh, continuous signal, or in the case of like NLP or something, you could go with discrete. So you could directly convolute it with U. So in this, the authors have claimed that even though this sounds good and it could be like parallelizable, like you could convolute like n times, like what you could do is like in recurrent networks, like you could have a dash one time or two time, one time here, and you could have imagine like you have 10 SSMs stacked upon each other. Instead of doing like the sequential one, parallelizable one will be like more efficient, like more like MHA one. So at this time, in theory, if you want to do a convolution style thing, you could easily parallelize it. But in the case of like SSM, you can't like parallelize it because that comes under stability issues. So so this in this side convolution, there were some problems when S4 was eventually announced. So at Haina convolutions paper, they eventually uh, came upon with this. Um, I'm sorry. Okay, they just came upon overcame this problem, and in the recurrent side, they kind of like told, okay, recurrent is like stable and it's fine because Mamba is using less parameters as well as you're getting some robust distribution with these gated functions. So why can't we like just use recurrent and go upon? So that's what they did in S5 and in Mamba. So the primer of S4 is like S4, you have this A matrix as hippo. Right now, we didn't see anything that is kind of like learnable, like the delta parameters or the A parameters, which is not like learnable, but you kind of like adjust those functions. Learnable in the sense you can technically learn this function, but it's not like randomly initialized as we say on a neural network level. So you kind of like initialize it. A function you can definitely learn in S4. Other B, C, and D, B, C could be learnable, but eventually they are also not initialized as random. They initialize as close to this diagonal matrix because the entire S4 thing is like more upon diagonalization, like more upon speed. So this is like the current thing of S4. So again, why there is a need for state space model? So eventually, like okay, I'm just a simple guy with like if I'm getting like if I need to put around much of this effort and get around 1 to 2% or match the performance of transformer, I'm not going to be excited because it gave me like too much work of it. Transformers, like you just spam this equation like softmax of QKT transpose by root T into V. This equation is like really good. So you don't need to learn much math, intensive math on it. But still, why we need to go for state space models? Transformers like eventually good, right? Like capturing what and all it is. But anyone like can anyone say like transformers like really gives you much of the compute easily, but still why there is so much hype or like so much interest over these state space models? So anyone from the group, please. Yeah, come on, guys. Like speak, say something. Like nothing is a wrong answer. Okay, okay. Even though like transformers could capture like what and all attention we get. even though like in transformer, whatever attention we get or something like whatever attention we get, it's really up to a shorter form of context. In the paper, in the S4 paper, transformers like in the really, really long task, long range task, transformer like really failed into it. Not even achieving like 50% of accuracy. 50% of accuracy is something like guessing, random guessing. So it's below 50% of accuracy. It's not even a uniform distribution at that point. So it performs really worse than a long context task. You may also say like eventually like state of the art right now, like it could really do needle in a haystack process, needle in a haystack data around 1 million contexts. But the thing is like expanding context even more, like 1 million, let us say like 1 billion or something. Eventually you can't go 1 billion, but a really high number, like more than a million. So if you want to go into that much context, eventually model will like hallucinate and say something random, which is like really not uh, really not feasible. So in the path text data set, what they did is like you have a data here and you randomly go with some paths. That's the path text data set. So these types of tasks, transformer like eventually failed, really failed, bad, because this path text data set, regardless of anything, it needs long range attention or long range context to perform really well. So that's why people are moving towards state space model, which promisingly showed more contextual understanding on the longer range than transformers. So that's it. So okay, I'm like let us imagine Morpheus at this um, matrix giving you two pills, like the red pill be convolution and the recurrent pill. Uh, so yeah, kind of fine, but yeah, I'm just thought it was funny. So let's go with the blue pill route, like the recurrent route right now, and then we'll go for convolution route when the time is feasible, like in the next session maybe. Okay, we start with S5 and S6. Eventually, it is a Mamba block, and how Mamba is used in vision and how you could use bidirectional Mamba, how it's used on vision. So we'll come upon that thing. Okay. So I didn't like. Um, okay, I'll just say. Um, in the S4 is like this A matrix could be represented with a set of eigenvalues and a diagonal vector and an inverse of the eigenvalues itself. And those diagonal will be belonging to the complex plane of P cross P, and the eigenvectors will be also be belonging to complex plane on P cross P. So this lambda is discretized by exponentiating with delta over here. So in the S4 process, we exponentiated with A bar is equal to A inverse. I'm just writing it square because it's inverse into something like, don't do it. Um, it's not like really, it's really wrong on the matrix perspective, but eventually you're doing squared, like inverse into, oh, I'm sorry, I'm sorry. Because transpose into this thing is squared. So this is how you discretize the A matrix on S4. But on S5, you discretize the diagonal matrix directly using this operation. So how they say is like it's selective because when you are discretizing, I told you like the discrete parameter is uh, hyperparameter or like initialized first. But in the case of S5, they made the delta parameters as linear layer or some kind of learnable function, learnable bits. So as I said, like in the before event or in the day, in now. Whenever you have something you want to do or you are having doubts on it, just parameterize the network. Like parameterize what and all it's possible. Either you'll get something good out of it or really bad out of it. But parameterizing these crucial tasks will like really help you towards it. Because on the case of parameterizing delta, it eventually lets you scan the previous input, as we said, like moreover, like parameterizing the forget get, because let me say how it comes. Because on the on the um, on the equation of recurrent networks, we eventually do this. So use being input and x is being like the previous computations. So parameterizing delta would eventually influence it. And while influencing with respect to the loss function, you eventually select the particular thing which is aligned towards the loss function. That's the right point. Aligned towards the loss function. You are selectively choosing the parameters, choosing what and all to take and what and all to forget with this uh, delta. So that's selective. That's selective scanning. I hope this was like understanding. So I'll come upon with this. This is the same stuff like x dot in the state space model is this. I hope you like told told on the previous session, and the same thing. What I said before, the same thing. In this case, in the S4, they initialize d equal to 0, but they initialize d equal to discrete of d equal to d here. And here they apply the same bilinear transformations over here. And then in computation point of view, this will be like nn parameter, and this is also will be an nn parameter, and this will also be an nn parameter. So we kind of like depended upon H hypometrics and came across from it, like came somewhat away from it by making it learnable. So hope it was understood. Okay. Okay, well, let me just say like, oh, okay, half an hour left. So I'll just
There's
say,
a very good diagram on the S5 paper, the internal structure of a single S5 layer.
yes, sir. I think I just added it, but let me check. I think I just added, yeah. No, 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 no. I added it. Give me a minute. I added with respect to like how it is. Okay. Sorry, like I added when I think like there was some technical issue. I'll just show you. No issues. Okay. Give me a minute. So, okay, I'll start from here. Okay. This is being S4 and this is S5. On the S4, like as I told, it was eventually based on diagonalization. You diagonalize it, some kind of parameters, let it be an n parameter for the sake of simplicity. You have it, and you compute xk from it, and you control y would be some kind of c times xk, and you have yk. You could apply some nonlinearity, get y, and you could just apply another mixing layer, like mixing layer more probably will be like, give me a minute. They told something on S4 or about mixing layer. Okay, let it be some kind of like a function. Give me a minute. Like a mixing layer will be like some kind of learnable function over UK, and you send those representations back into the stack. This thing. So that's it. But on the SY paper, you don't have a diagonalized matrix explicitly, but you kind of like diagonalize it using V transpose. So you have this. This is also an NN parameter. Speaking on practical point of view, you apply the recurrent formula and get it, and you apply the control gate, and you apply nonlinearity, and you get the UK back into before. So I hope like this is understandable. Let me just compare with LSTM point of view. You have like a forget gate and remember gate. You have an input here as well as output here, and the input from here, and you'll do some kind of multiplication here. I'm not like really right because I don't like remember it. And you mix your outputs and get it into hidden state, as well as on the output state what you get from here. Like you have an output gate here, sorry. So it's, if you look into LSTM, it's more like kind of it. Like you could say this is some kind of like forget gate, and this kind of like some kind of remember gate, and you do a nonlinearity function over it and get those output put back into stack, and you kind of like keep track over it. Hope it's understood, guys. Okay. That's the S5 paper over there. So having SSMs in the, if you come into Mamba, they don't only have an SSM over there. They have a linear projection over data, like they kind of like mimicked into transformers. They have a linear projection into data, followed by S5 layer, followed by S6 layer, and followed by another linear projection, which is increasing. So kind of like a transformer point of view on the recurrence side. So I'll just show you. Yeah, this is the thing. So yeah, this is just branching out the input and applying silo function, but you could eventually do in SweGLU or SweGLU or silo function, anything is fine. You just go into, like, you branch out those inputs. These are like linear projections, NN dot layers, and you apply a convolution block over there, and you apply a nonlinearity again. The nonlinearity here is like silo, and here to silo, and you apply SSM block, and you multiply it, or hammered multiplication. But if you applying like getter linear unit activation functions, you don't need to multiply it. Like you just you eventually you will multiply it and do it on the getter linear activator function. But if you're using silo and everything, you have to do manually. Yeah. Even in getter linear, you do manually, but kind of the same thing. So this is called as hammered product, and you multiply it, put it into a NN dot linear layer, and get out the projection. So that's the Mamba over there. So let me say on restrictions of S5. S5, you only have SSM layer with selective delta, which is learnable. A is learnable, B is learnable, C is also learnable, and D is also learnable on S5. But on S6, you have an A, which is learnable, some kind of NN dot parameter, and D, they didn't mention here, but on the practical implementation of papers, they also made D, which is NN dot parameter, and BB, linear projection of the input. C also being the linear projection of the input. And you discretize it with delta, and discretization, I'll come upon that. And you apply an SSM operation, like you have A bar and B bar and C bar, and eventually D2 on the practically they kind of like implemented with D2 with an option. So with these, like you put the recurrent equation and get Y. Get Y back. So that's the thing. So discretization, same as like what we saw before. A bar is discretized into e power delta A, and B bar is discretized into delta A inverse. Give me a minute. So B bar is like exponentiating with delta A minus I with delta B. So this is it. But I told you like these things. The first thing is like you can't eventually use the A and discretize it because like this really big matrix and B2. So why there is an hype for Mamba? So I told you these things like A bar and B bar essentially like same with SSM. But even though when we come to SSM, uh, nothing like S4 or S5 like really didn't take off much. Why there is an hype now when it comes to Mamba? Anyone can just say. No issues with that. Like with your own thoughts. Okay. Anyone? Like anyone wants to say anything with your own thoughts? Like anything. Let it be.
Could you repeat the query here?
Okay. Okay. The thing is like SSM is there. SSM really performs well on long range tasks. Why there is an hype for Mamba? Like it wasn't like in before S4 or S5. Like people are going crazy with Mamba right now. But why?
I think so with the Jamba, with the Mamba's MOE layers, they
Hmm.
were able to extend it. Uh,
Okay.
so
Okay.
I was
That's kind
thinking
of a good.
majorly from the practitioner's point of view of how,
Hmm.
yeah, they were able to scale it up.
Yeah. How could they? Sounds like a dumb question, but the thing is like, how could they scale it up? What's the reason behind it? That's what made the hype for Mamba. You
Okay,
could get me right.
Hyper
We could
Mamba.
scale it up. Yeah, hype for Mamba, not hyper Mamba.
Okay, okay,
That's the
hype for
hype for
Mamba.
Mamba.
Okay.
Okay. How could they scale it up? Like, how could they scale the recurrent thing into MOE like architectures? Like, if it's for transformers, yeah, we could understand it runs in parallel. But for the recurrent one, you don't really get to run in parallel, as we say. So the hype for Mamba is like justified by making this thing. Okay, before like spilling into hype, let me say flash attention. So back to some computer architectures class. So let me say I have a CPU here and I have a RAM here. Okay, and I have a cache here. So even though RAM provides me like a really good amount of memory, the throughput between the RAM and the CPU is like really low. And when it comes to cache, the the throughput will be like really high, but the memory is like really low. Am I right? So what they did is the same as CPU. In GPU, we have something called SRAM, HRAM. SRAM will be around 20 megabytes, and if you're like doing in some kind of like really big graphics card, it's HRAM will be around like 20 gigabytes or something. Yeah. So HRAM gives you really high computer storage, but SRAM gives you really low storage but really high throughput. So in the flash attention, what they did is like by calculating KT transpose, you can't like do it in SRAM because it will be really high. So you kind of copy it, the individual parameters, compute it in SRAM and store immediately in HRAM. So you kind of do that thing. So in Mamba, everything here is computed on SRAM. So thus giving us really high speeds on these kind of tasks. So that's why like hype for Mamba is like you could scale it up, you could scale it up because eventually these major operations are sent to SRAM and stored it back, same like in flash attention. Um, so you could like get incredible amount of speeds with the parameters available, and you could also scale it up too. So that's the hype for Mamba and why everybody is like growing crazy on this. So okay, so yeah, this thing, the only state space thing. But can we like increase into like some kind of forward and backward in like in LSTM? Like in LSTM, we have something called bidirectional LSTM. Bidirectional LSTM will like go forwards and backwards, like concatenate it and put it into some kind of like a single entity. So in Mamba for vision as well as in bidirectional Mamba, I'll cover that thing. So right now, like if there is any doubts or any queries related to Mamba. I hope there is no queries, or if there is any queries, just let me know. Okay. So extending Mamba into vision. So vision is like images like we all know that it belongs to real number domain when you normalize it. 234, the height, width, and 224. Sorry, height, width, and channels. Yeah, the same normal stuff here with the vision. But in the vision Mamba, what they did is like they kind of like came with BERT-like approach. So in BERT, like you patch up and put a convolution with the dimension of let us say 768, let it be, and you apply convolution and convert it into uh, one layered one layered vector with the dimension what we need, and you kind of like use tokenized way of applying transformers. Like that's vision transformers. So on Vision Mamba, you kind of like do the same thing as in Vision Transformers. This is the same thing, and this is also the same thing. So in Vision Mamba, the thing which differs from it, like the forward and backward SSMs. So on forward and backward SSM, how we do forward and backward, I'll come upon with that. The same as the Mamba, like the same thing as Mamba. So forward and backward. So on forward and backward scanning, it means like this is, if you go in this way, this is forward. And if you go exactly in the opposite way, this is backward. So in technically coding point of view, what you do is like you take this and you reverse it and put it here, and you compute those operations and you get the output back. You know what you get, right? What I'm saying?
Yeah,
You
yeah.
eventually like, yeah. From the forward and backward, like you add it and you put it into projection, and the residual connection, same as transformers, is there. So people eventually came like, why can't I just go forward and backward? Why can't like go crazy like forward and backward, upward forward and upward backward, something like this, and back again, and cross scan. So just saying like you could go cross by cross on the image, like something like this. So that's how the Mamba has evolved. So uh, that's kind of it, how Mamba is and Mamba is developed. Mostly a cameo, let me say.
There's a vector too. I looked at the code in the forward convolutional 1D part.
Yes, sir.
But I was unsure of the vector. I mean, there was a parameter there. So if you
Yes,
find that, or
like
I will post that in this
mm,
uh, Discord,
sure.
and we can discuss about it later.
Yes, sir, sure, sir. Like as far as like I read in paper and code, the same BERT-like thing. This will be like one-dimensional vector, so you can't do two-dimensional convolution. Like the one dimension you are constrained to. There is no reshaping or anything. You just project it and do the convolution and apply the state space operation. Like let us see on the
Okay.
code part. Okay, sir. So this is like the Mamba which just came upon. The the obvious like the, let me say, the cameo or the honorable mention is H3 paper. H3 is like Hungry Po matrices. Hungry Po is like just I'll come upon with this thing. So uh, just applying transformers basically into SSM. So they kind of like came upon with adding SSM here and a SSM at the Q value, K and V. You kind of like do the Q value over there. But the most interesting thing they came upon with making attention linearly recurrent. So you kind of like let us say instead of using softmax, let us say we are using a similarity function, similarity of QK into V divided by the sum of all similarity from the previous and VS. That's it. So this is the linear attention which they came upon. So when looking into this, like you could really scale the attention into recurrent point of view, and that's also an interesting case of development. And let us see how they come upon with this. So then another thing is like Griffin. Oh, shit. Give me a minute. Yeah. which applies state space blocks in MHA as well as in MLP. So kind of it, but not into Mamba. But it is also like they claim to perform really well than Mamba, but it's Google. You're saying like I don't believe in them on metrics. So that's just me. I'm just fine. Okay.
Sorry, you were unclear a bit earlier. Could you repeat that?
Just Griffin is like just an MLP. Like MLP, you apply MHA block as well as with MLP block. Yeah, this is the transformer side. So in the MLP block, they have employed mixture of experts, and in MHA block, they were employed SSMs. So that's Griffin. But they
Okay.
claim to have superior performance than Mamba, but it's the Google we are speaking because I don't really trust them on metrics from the era of vision transformers. So yeah, yeah, this is the vision Mamba algorithm. First, you normalize it and you convert those thing into linear projection, and the Z will also be a linear projection and with an activation. And now for forward layer, you apply silo convolution, linear projection and linear projection. You parameterize it with this formula. So log of 1 plus exponential of the linear projection of x into some kind of delta plus the parameter like let it be some kind of like initial parameter to start on, like let it be delta equal to 0.1. So parameter to start on, and you have this. So you compute the same thing, multiplying that with mm, that with n and dot parameter for A, and for B naught you have this, and you apply Y naught to get uh, apply SSM to get Y naught, and you in the for loop. And with that, you apply the product from the Z into this and the same as this. So you add it eventually with the residual connection and you linearly project it. That's the same thing, but you're just adding then another layer and adding a backward SSM and you're just adding it. That's it. So that's pretty much it on how we came upon with Mamba and Mamba for Vision. And you kind of like, I think you guys had a primer on this thing. So yeah. On Vision Mamba side, there is also a thing called VSS, Visual State Space, which is also a direct interpretation of Vision, just a transformer block. You'll have a VSS block here. And in the VSS block, you just have the Mamba blocks inside it. And instead of like doing in Vision Mamba, VSS would be having employing like a transformer like architecture. This is MLP and add a norm, add a norm. Yeah, same as that. So that's pretty much it. Thank you very much. I hope this, if there is any doubts, like come upon now. Okay, I got a chat. Thanks. We use Mamba. Okay, when should we use Mamba and when should we use transformers? Okay, that's a really good question. So, okay, for the industrial point of view or for the fine tuning point of view, what I really prefer is like right now, as far as 2024, what I do is like instead of taking a lot of risk and doing into something, like we know the process, like for fine tuning into something, what I really do go for is like for the transformers. But when would I go for Mamba is like, is something like you have to train from the scratch or train from the scratch. That is advisable to go with Mamba. But if you want to go with like, let us say like you want to build something chatbot from a transformer based model or Mamba based model. Right now in the industry, we don't have much of Mamba based models for practical use. Like in academia, it has come, but it would take some time for get into practical use, and fine tuning it on transformer space is like really easier than fine tuning on Mamba space, because we don't have like LoRa or Dora or some other fine tuning strategies, which eventually reduces the number of parameters. But on Mamba, right now, yeah, it will change eventually. But right now, what I say is like, if you want to train from the scratch, you can go with Mamba. If you want to fine tune in NLP space, the mostly like we will do the fine tuning thing, you can go with transformers. Transformers uh, from the available models such as Llama or Gemini or GPT. If you want to train from the scratch, what I would say is like go with Mamba. Yeah. Hope it was like uh, understandable. Thank you. Okay. If there is any doubt, anyone?
I don't think there are any more doubts, and so should we
Okay.
just wrap it up?
Yeah, wrap it up. Yeah, I'll just give an end notes. Thank you. First of all, let's all thank Himanshu for his contribution. Like without him, like there is nothing possible. Like half of his slides are his, and I'm really like thank you all for attending in this meeting, making it kind of interactable, and it was really good decoding this paper. Thank you.
Thank you, Madhav. Your explanation really goes a long way in helping me personally, understand these papers. So thanks a lot for, first of all, working with me and presenting these papers. It's just amazing to have you present.
Yeah, thank you very much.
Do we extend this to the derivative work of Mamba in the next presentation, or do we go a different route?
We go into like if like let me speak practically, like if we go like expanding on it, like it will take ages. Like the rate of research going on AI is like really huge. So the thing which I came upon is like giving you a primer on what and all is available, and you could like explore from this point on. The next route of this presentation will be on the convolution side of SSMs, high convolutions such as Haina convolution. So the next route will be on convolutions route.
Okay.
Yep. I'll ask with Raj sir whether like we are like hijacking this session for like 3 weeks straight. So let me ask Raj sir whether it's okay to present next week or some other week. Yeah. If there is like any other questions in the chat or in the mic, anyone? No. I hope like everybody have a great day watching this or in the meeting. Let me know if there is any doubts in Discord. I'll be more than happy to address the issue. Thank you.
Thanks, guys.
Thank you, sir. Thank you, Mansu. Take care.
Thank you. Thanks, man. Take care.
Yeah, man.